now we're going to look into the navel a little bit here and look at some of the really fine details of organic aerosol formation processes in ozone. And this is what I'd like to show you today is just a set of research that's been done in my laboratory looking at the isoprene photochemistry and then trying to use the updated information to understand what's going on in the atmosphere. So it turned out to be too big a topic for 15 minutes. And so today what I'm going to do is just focus on the alkyl nitrate chemistry, in particular the formation and loss processes and the impact on NOx. So this was a calculation that was done by Fabien Pelot in my research group a few years ago, where we did just a simple experiment and said, what if everyone emitted NOx like North Americans? What would be the response in total tropospheric ozone? So this is the ozone column response. And what I hope you can see from this figure is it's enormous in the tropics. That is to say that if everyone in the tropics emitted NOx like us, tropospheric ozone columns would go up by 25 to 75%. So this is not a small effect. And so why is that? This is really classic NO-limited ozone chemistry. And so I'll take you through that just very briefly for those of you who aren't chemists. If we assume an R here, which is an organic molecule such as isoprene, it's oxidized in the atmosphere by OH to form these peroxy radicals, RO2, which then undergo a set of reactions with NO, first to form aldehydes and HO2, and then to go on to reform the OH radical. And in the process, we convert NO to NO2, which is then photolysed to form ozone. So the first thing you shall see here then is that when you have large amounts of organics combined with NO, you expect to form ozone. So why does this depend then so much on the NO concentration? And the reason is that there's a competition for the oxidation of the peroxy radicals. They can react either with NO or they can react with other peroxy radicals, in particular HO2, to form peroxides. And so now the question is, what's the branching ratio? In other words, how much of the peroxy radicals react with NO versus HO2? And in general, in the tropics, there's very low NO concentrations, and as a result, we tend to mostly go to peroxides. So then as we add NO to the atmosphere, we essentially can very sensitively drive this chemistry towards oxidant formation. So what does this have to do with the formation of nitrates? So in the first figure I showed you earlier, we had all of the RO2s reacting with NO to go on to form HO2 and aldehydes and so on. But it's a little bit more complicated, and that there's a channel from these peroxy radicals that lead to organic nitrates, here listed as RONO2, and they have varying yield depending on which molecule it is. So then what happens to these organic nitrates is the question, and there's really two possibilities. One is that on some time constant, tau NO2, they are converted back to NOx. Another possibility is that on a different time scale, tau nitric acid, they're converted to nitric acid. And so now if we think about this, what matters is the yield, that is to say, how efficient are we at converting to these nitrates, and what time constant do they go on to form NO2 or nitric acid. And that will then determine the potency of a given R molecule towards forming ozone. If we efficiently go down the path to nitric acid, then essentially the chemistry will suck the NOx out of the atmosphere, and the response will be minimal. On the other hand, if the yields are zero, then the chemistry is most efficient. Or if we have a significant alpha, but that these nitrates are just converted back to NOx very quickly, it essentially doesn't matter. And so that's what we've been working on in our lab, and that's what we've been working on in the field to try to understand these time constants and try to understand what is the yield of nitric acid essentially from this chemistry. Okay, so in Fabien's paper, we did this other experiment where we varied what we thought we knew about the formation and loss of these alkyl nitrates. And that's what's shown on the x-axis here. That is the change in the nitrogen oxide concentrations here from -40 to 40. Very large effect by just changing how you deal with that chemistry in a model. And then this is the effect on ozone production. And what I hope you can see is that the effect that this chemistry, first of all, can have a very large change in the ozone production, but also that it really is the dominant question for isoprene chemistry. It really is what happens to these nitrates. Because if they are efficiently converted to nitric acid, we end up down here. And that is to say that isoprene is not as strong a forcer of ozone and oxidant as might expected in the base case. Whereas if we say it's very efficiently converted to nitric acid, if it's a very efficiently converted to nitric acid, we end up down here. If it's very inefficiently converted to nitric acid, we're up here, and the chemistry will be very, very hot. Okay, so let's go to the lab first. One of those parameters that was in Fabian's model was the yield. That is to say, what fraction of these nitrates what's the fraction of nitrate formation in the isoprene mechanism. And so what I plot here is data from the lab. So this is formaldehyde concentrations as we oxidize isoprene. This is by Frank Koentz's group. And then this is the sum of the first isoprene nitrate and second generation nitrates from isoprene. And what we can see is that the correlation is beautiful and that the slope is around 0.17. If we work that out, that tells us that the nitrate yield from isoprene plus OH is pretty high, around 13%. This is certainly at the high end of what has been previously recorded in both laboratory measurements, although there are other measurements that support this value. The second thing is what I show on the right side, and these are GC chromatograms where we're able to resolve the isomers, and this is a little bit complicated, but in blue is what's shown as if you have a typical laboratory experiment where you put a lot of NOx in the chamber. And what we see is that we form a lot of these, what are called deltas, where the OH and the nitrate are 4 carbon atoms apart from each other. Whereas if we go to something much more like the atmosphere, which is shown in red, this is where we have RO2 lifetimes that are getting up towards where the atmosphere really is. What we find is that almost all of these nitrates are what are called beta nitrates, where the OH and the NO2 are just 1 carbon across. And indeed, almost all of them are in this one here, this tertiary nitrate, where the OH and the nitrate group is on this 3 carbon tertiary nitrate. This seems very just sort of a small detail, but as I'll show you later, I think it's paramount. Okay, so the nitrate yield is high, and that we're going to see that these tertiary nitrates are the majority of the nitrates formed. Becky Schwantes will have a talk later where she'll talk about the nighttime chemistry that we've been doing in the lab. Okay, so let's talk now about what happens to these nitrates once we make them. First thing we've done in our lab is, and this is a collaboration with Ron Cohen's group, Lance Lee came to our laboratory, and we measured the rates at which these are converted first to the carbonyl nitrates, the C4 nitrates. So OH essentially reacts with these nitrates quite quickly, and they end up being converted into these carbonyl nitrates. And the time constants here I want you to look at, of order 1 day for what we think is the major one, and of order about 4 hours for this other nitrate. So they're actually quite quickly converted from these C5 nitrates to the C4 nitrates. That's the first thing we've learned in the lab. The next thing is that these nitrates, these carbonyl nitrates, they could also come from from oxidation of MVK and methacrylin, which are the major oxidation products of isoprene. But in our lab, we've learned actually that these yields are very, very small. Only 4% for the MVK nitrate, and in the atmosphere, less than 1% for methacrylin. And what that means, then, is that these nitrates, these carbonyl nitrates, almost all come from the oxidation of the primary nitrates, from those that had come directly from isoprene. Mueller and Peters et al. In a paper in 2014, I think convincingly show that these second-generation nitrates will be photolyzed very quickly, time constants of less than half a day, and that these will almost certainly release NOx again. Okay, so what do we see here then? What we see is that the yield is high, but the lifetime of these is quite short, probably less than a day, for these isoprene nitrates to be converted back to NO2. And so if OH oxidation rules, then we are going to have a minimal effect of this chemistry, and the chemistry will be very hot. In other words, isoprene nitrates will probably not be a significant way to titrate NOx out of the atmosphere. So now I want to turn to this time constant. And what we're going to have to see is that this is going to have to be competitive with this if we expect the nitric acid formed from this cascade to be important. Okay. So the first thing we might think about is deposition. So we can imagine these nitrates are deposited to the trees and then converted to nitric acid. So we actually were able to measure this deposition velocity during SOAS. So this is our experiment was up on top of this walk-up tower in Brent, Alabama. And Alex, Teng, and Tran Nguyen were responsible for these data, and we did eddy covariance flux measurements of a whole suite of oxygenated VOC coming from the isoprene chemistry. And although you probably can't see in the back, these are for the isoprene nitrates and the MBK nitrates. Deposition velocities averaged over a day are about 1 centimeters per second. So is that a big or a low deposition velocity? If we take a 1,500 meter boundary layer, that turns out that the lifetime with respect to deposition is of order 2 days. So this is likely to be important and may be competitive when the OH concentrations are low. But generally, it's not going to be terribly important. Deposition is likely not to be a major loss, although because it makes nitric acid, it can still be important. So now let's turn to ask how well can we put this all together. So here are data that were obtained during Seekers. This flight of, I'm going to focus on is September 6th, where we flew back and forth across the Ozarks. Armin Wisthaler measured isoprene, shown in colors here. This is this really hot zone. Some call it the isoprene volcano. I don't know if Daniel Jacob made up that name, but this is a very hot spot for isoprene chemistry. And what the plane did was to fly from the east to the west across, and then turn around and went back, and then went back and back forth at different elevation or altitudes above the ground. And what we can see is that as we flew on the eastern side, there was a lot more NO. These are measurements for Tom Ryerson and the NOAA group. So there's about 100 parts per trillion on the east side, and then 50 to 20 parts per trillion of NO on the west side. Okay. What's shown in the bottom here is the isoprene concentration, so elevated everywhere, up to 5 parts per billion out to the west, much lower in the east. I won't have time to tell you about why that is, but that's because there's a lot more OH on the eastern side. So this idea that OH is high, is sustained in low NO environments is just completely unsupported by these data. Okay, so there's much more OH when there's higher NO levels. Okay, so recall from the laboratory, we took this measurements of formaldehyde, we plotted them versus these nitrates, we got the slope, we came up with something that was around 0.17. If we go to this data, first of all, we see it's extremely well correlated, and the slope is a quarter of what it was in the lab. Okay, so it's 1/4. So now turning to a quick speculation. What is going on here? So one possibility, of course, is that there are additional formaldehyde sources. And of course, there are additional formaldehyde sources in the field compared to the lab. And we've run a box model, and that can explain only a small fraction of this difference. And here is what I think is happening. What I think is happening is that these tertiary nitrates are being lost to nitric acid on aerosols. And this is a suggestion that Glenn Wolfe will also elaborate on, and is quite consistent with the flux data. Matt Elrod at Oberlin has shown that beta hydroxy tertiary nitrates, i.e. the ones that are made in isoprene photochemistry, are hydrolyzed very rapidly in water. What I mean rapidly, I mean they don't live for more than a few minutes. And given the aerosol surface area in the Ozarks, we would have to have a gamma of around 0.04 for these nitrates to explain the data. It's fast, but that's about the same as N2O5. And there's more to come. This is really important, because if this is true, it means that the isoprene chemistry is incredibly efficient at removing NOx from the atmosphere, and it will really alter how we understand isoprene chemistry in general. So I am going to stop here. I'm going to tell you that laboratory and field data have substantially reduced the uncertainty in our description of the gas phase chemistry and the deposition dynamics. However, these data are inconsistent with the apparent short lifetime of these nitrates in the atmosphere. And we really need to go back to the lab and do some new experiments, try to understand the heterogeneous uptake of these nitrates. With that, I'll take any questions and just put up my acknowledgement slides.
Thank you so much, Paul. Let's have one quick question.
Paul?
So the hydrolysis rate constants for at least some organic nitrates seem to be quite pH dependent. And I'm wondering what you think about it. You have very acidic aerosol, lost by aerosol.
So the question was about the role of aerosol acidity. And I'll say in Matt Elrod's experiments, he showed that for these tertiary nitrates that they were not pH sensitive, that they were very fast, independent of pH. I think for the other nitrates, it's very likely to be the case that they are pH sensitive. But I don't know enough to speculate.